Hello and welcome to the University of Calgary webinar, Leaving Carbon Behind. My name is Jennifer Alford and I will be your moderator today. We'll meet our scholars in just a minute, but first I just want to give you a little information about what we're doing today and how it all works. Now these webinars feature a series of University of Calgary scholars who are kind enough to bring us a summary of their research. We ask you to ask questions throughout the course of the webinar. You can see the little box there, just type in your questions, and we'll try to get to as many questions as we can. We also have a few resources on this topic, so you can check our resource list. And if you've been on waiting for us to start for a few minutes, just refresh, because we've actually just added a resource while we've been waiting to go live here now. We've also asked you to keep the conversation alive on Twitter, if you happen to be on that medium, using the webinar hashtag #ExploreUCalgary. And at the end of the webinar, in about an hour, we'd ask you to take about a minute to answer a very brief survey just to help us see how we're doing as we go along with our webinars. Now, let's meet our scholars. First, Joule Bergerson. She's the Canada Research Chair in Energy Technology Assessment, and she does research that focuses on developing systems-level tools to investigate economic and environmental impacts of energy technology. So we'll hear all about that in a few minutes. Marc Strous is the Campus Alberta Innovation Chair. Oh, I got to change the slide. Sorry. Marc Strous is the Campus Alberta Innovation Chair in Energy Bioengineering in the Department of Geoscience, and his research focuses on using microbiomes for energy conversion. He's discovered and commercialized a whole bunch of new bioprocesses. But before we get going with that, we just want to ask everybody to take a second and answer this poll question, just so that we know who it is we're talking to out there today. So tell us a little bit about yourself. Are you a researcher? Are you a student? Do you work in the field of energy regulation? Do you work in the energy industry as a whole? Or are you just someone who's interested in this topic? So just take a second there, please, and click whichever box fits best with you. And we will go to our results and see. Okay, so we've got a lot of people, almost half, who just have a general interest in the topic, which doesn't really surprise anybody in the room, I don't think, hey? And quite a few, nearly 40%, who work in the energy industry. All right, so we have a little bit of a sense of who it is we are speaking with today. Thank you, everyone, for playing along. So, Marc, the global climate is changing.
Yeah, so there's been a lot of, so hello, everybody. There's been a lot of talk about changes in the energy system. So I would like to begin with reviewing some of the evidence that is leading to that. So what you see on this graph is a graph of the CO2 concentration in the atmosphere during the past 450,000 years on Earth. And what we see here is that the CO2 concentration goes up and down with the ice ages, high between the ice ages and low during the ice ages. And then suddenly we see this fantastic change that is a straight vertical arrow at our time where it just suddenly bumps up to 400 ppm, so parts per million. And to just see that in context and think about how fascinating that is, I put a arrow below the graph that shows how long we already walked this planet. And there was some news last week that perhaps human remains were found that are 300,000 years old. But what we can say is we as humans have never seen something like this before. So it's really a new problem. So that's totally clear. And then scientists have done a lot of work to try to understand what causes that sudden increase in CO2. And as far as we understand today, it seems very, very likely that our emissions from burning fossil fuels are responsible for that change. Now, all the talk internationally needs governments to implement new policies, and I've shown some examples of that in this slide. So a couple of weeks ago, the world's largest offshore wind farm opened in the Netherlands, 150 windmills producing enough electricity for 1.5 million people. There's 2 more of those farms planned for that country. So that's really significant change. Another thing that is happening is a lot of governments, like the government of Alberta, are implementing policy to put a price on carbon, and that way they try to make people make different choices and have them burn less fossil fuels in their cars or in their homes. And another really important trend that gets a lot of attention is the rise of electric cars. Are electric cars gonna take over the world at some point? Nobody knows, but it's certainly a trend. And the projections are that somewhere, between 2020 and 2030, electrical cars will be as expensive or cheap, same price as the petrol cars. So that's really an important thing, especially for this province and this country that is so that made such a good living so far by exporting fossil fuels.
Marc, before you go on, we have a question with the graph that you showed us at the beginning with that blue arrow. We can just go back to it here really quickly. That shows it at 400 there. Is that from hard data or is that from a simulator? Do you know?
So the CO2 data is totally hard data. Very easy to measure the CO2 concentration in the atmosphere. So there's absolutely no simulation in that.
Got it. Hard data. All right. Thank you.
All right. So it's clear that we have to adapt, and it's really critical as a country and a province that we move technology forward to stay competitive and hang on to our wealth. And the government is also stimulating that. So, for example, here at this University of Calgary, we recently were awarded a $75 million research grant to work on this energy problem.
And these are some of the things here on the right that we're that grant is looking at?
Exactly. So this grant has three pillars. So one focuses on the oil sands and mainly focuses on reducing costs and reducing environmental impact. The second topic is on tight oil and gas, so that's commonly known as fracking. So we also have a lot of resources in Alberta and BC that could be accessed, but there's concerns, and those concerns are totally genuine about induced seismicity, so earthquakes, about stray gas getting into drinking water in the subsurface, and also that technology could be improved. So that's another pillar. Mm-hmm. And finally, and I think that's most of the topic of today, leaving the carbon behind. So can we do something about that CO2? Can we convert it, or can we get let's say energy from fossil fuels without bringing any CO2 in the atmosphere?
And just to be clear, as you said, we're going to discuss that third bucket today, and the other two, the oil sands and tight oil and gas. We're working on it, but that's not our topic of conversation today.
Exactly. So maybe there will be another webinar about that at some point. Okay. So looking at that research that we try to bring new technology, there's three topics, and I'll talk a bit about all of them. So the first one is the extraction of electricity from reservoirs. So a reservoir, a fossil fuel reservoir, oil beneath the ground or oil sands, can we, instead of extracting carbon, directly get electricity from that, which would be very convenient for all those electrical cars.
I was going to say, yeah, those cars need that electricity.
Second one is climate neutral synthetic fuel. So that's a pathway where we take CO2 from the air, work our magic, and end up with gasoline, diesel, or jet fuel, which would get burned and bring the CO2 back into the air. So it requires no changes to all the infrastructure, but it also doesn't remove any CO2 from the air. Third one is called bioenergy with carbon capture and storage, and that's where we also take the CO2 from the air, convert it to biomass in this project with algae, microorganisms, and then the biomass gets converted to methane, which gets burned in a power plant, and finally concentrated and buried below ground. So that would actually be able to reduce the CO2 in the atmosphere.
Okay, let's learn more about all that.
All right. Well, so looking at synthetic fuels first, so I realized this slide is a little bit complex. It shows how it works. Basically, the CO2 gets captured from the air. There's a couple of companies already at the pilot stage with that technology. And then we used a solid oxide electrolyzer cell, and that's actually the main topic of the research to improve that technology. But the CO2 gets with electricity, so it would have to be renewable electricity. The CO2 gets reduced to carbon monoxide, the CO. And then the carbon monoxide, together with hydrogen, goes into very classic refinery type processes. First, efficient synthesis, and then all kinds of upgrading and refining. According to the estimates, efficiency is 55%. Overall cost at this moment, 2 to 3 liters, is still significantly above what we pay at the pump today. So it's clear that that has to be improved before it has any market potential, and that's the aim of this research. Now the second one is the bioenergy topic. So this slide shows the corn field. So corn has been the largest bioenergy project in North America. So the United States produced a lot of bioethanol from corn. It's really challenging to make a difference with a process like that, because you have to put a lot of energy into this whole process. So from growing the corn to producing the ethanol, you don't get much net energy out of it. So that clearly doesn't work so well. And one of the reasons why this is so expensive and energy intense is that when you have a field, it doesn't stay a cornfield by itself, right? If you would not put in all that energy, it would look more like what's shown on the next slide, a large field of weeds. And these weeds are much less cost effective, much cheaper to grow, but of course they can't be refined to bioethanol. So that's kind of a concept we're taking to our algal biotechnology. So when you look at algal biotechnology, the nice thing is you can have a fantastic productivity per area of land. So you don't need so much land. You don't need you can use marginal land or deserts, but it's very expensive. And again, one of the reasons why it's so expensive and energy intense is that all these projects use monoculture. So they try to grow a single type of algae in those systems, and that is really tough to do.
Because you need the right agriculture and the right land and the...
No, because if you don't take proper measures, you'll get invading organisms, and they will eat those algae.
Gotcha.
So you have to make a lot of effort to keep those other organisms out, just like you need to make an effort to keep weeds out of your cornfield. So our approach, one of the innovations we're using is we're not using one single strain. We're using essentially, let's say, algal weeds. Whatever grows in there is welcome, as long as it produces. And that was quite an interesting innovation to push through, because those people had absolutely no confidence in that. But recently we published our first results, and we show that actually our weed algae, our microbiome is much more productive than many production organisms. So it actually works. So I think that's one of the key steps for making this bioenergy cost effective. Now the final one is the production of electricity from the oil fields. So I would like to briefly review how oil is formed below ground. So in the distant past, millions of years ago, there were marine plants, animals, microbes, very productive system. They settled to the floor of for example, shallow ocean. They accumulate there. In the end, they get covered by mud, more mud, pressure builds, temperature builds, and then those remains of those organisms get converted to oil. and the oil then moves from what they call the source rock to the eventual oil reservoir. Now, it's very important during that process that the temperature and the pressure are high enough so that all that old biomass gets sterilized. Because oil is actually really nice food for microorganisms. So when it doesn't get sterilized, it degrades. And one of the largest examples of what it looks like when oil degrades is our oil patch in Alberta. Right? It didn't get sterilized properly.
In the oil sands, like in the bitumen, you mean?
Exactly, yeah. So that's the kind of the end product of microbial degradation. And that's also that microbial degradation is also what we want to use in our process. So the important point is microbes can use oil as a food source. And when they have something to respire, like oxygen or sulfate, they will burn it all the way and will produce carbon dioxide.
So just to clarify, so crude oil, like a high quality crude oil, doesn't have the micro or many.
I think, let's say when as soon as we start getting that oil out of the ground, we will contaminate that reservoir, right? So the microbes are there,
right?
But they haven't been there for those long periods of time
underground.
To do all that. So this shows one of the schemes we're exploring. So there's a couple of them, but this one is the most easy to understand. So during oil production, what happens is in the beginning, maybe the oil comes out spontaneously, but at a certain moment, the reservoir pressure is lower, and to get the oil out, we need to add something to push it out, which could be water. CO2 could also be used. But already in Alberta has many, let's say, oil producers that pump around water through reservoirs, and maybe only 10% of the volume that is recovered at the surface is oil. So in our scheme, we're also going to use that exact same setup. We're injecting water, but we're adding to the water an oxidized, what we call electron shuttle, and this could be an oxidized form of iron, like rust, or manganese. This iron or manganese gets pumped into the reservoir, and then the reservoir microbes will love that. They will start oxidizing the oil, producing CO2, and reducing that electron shuttle to its reduced form. And then the reduced electron shuttle gets produced at the second well, together with some oil probably. And the reduced shuttle is an energy source, right? So it could be used in a fuel cell to convert that into electricity. Shuttle gets oxidized again and gets re-injected. And because all the conversions happen below ground, the CO2 produced in the reservoir will stay trapped under the cap rock. So that's one of the ways you could, in theory, produce electricity from a reservoir, and then of course the research is addressing and what we maybe can show in a few years that it works or that it doesn't work.
Hopefully that it works. So is this being tested in the lab, just in the lab now, or in the field, or in the lab?
So this is being tested in the lab.
And then it would take a couple of years to get it out into the field and test it there?
Well, this particular scheme would be relatively easy to take to the field because there's already so many of this type of setups there, right? And I think it's a nice opportunity to would work with conventional production of oil. You don't exactly deplete the reservoir. A lot of oil remains behind. It's no longer economical to produce. So I think that would be an ideal setup to test it.
And you could use it with reservoirs that are like the old reservoirs.
Exactly. Yeah.
Huh.
Okay, so the key takeaways from my little talk. So global climate change, a lot of gets a lot of negative press, but I think we should also consider it an opportunity for innovation and economic growth. Right? Things are changing. If we get there first, we'll be able to do good business. There's a very good chance that greenhouse gas emissions reduction, so the need to do so, might lead to a partial electrification of transportation. I think that should be considered a threat for any oil-producing nation. So the University of Calgary is exploring options to produce climate-neutral fuel, and green gas, so what I showed you with the bioenergy project. And we're also exploring the possibility to use reservoirs, let's say a giant battery, getting electricity from them instead of oil, and that's going to be a combination of microbiology and materials.
Wow. Okay. Not surprisingly, we have quite a few questions. So, one person is asking, could CO2 conversion processes replace the biopathways for carbon-neutral ethanol production?
Yeah. So I think if you ask me, that's quite likely. So it depends a little bit on geography. When you look at Brazil, it has quite a successful bioethanol, let's say, process. So lots of sugarcane is converted into bioethanol, and it has quite a good energy return on energy invested. So that geography works very well. But not many countries have as favorable conditions as Brazil. And so when you come to North America, the synthetic, let's say the chemical process, has, I think, a good potential, especially because with this chemical process, it's much easier to tune the product so that you can meet all kinds of specifications that are there for fuels, which are much more difficult to meet for bioprocesses. But bioethanol is a simple product. When you go to biodiesel, it becomes really much more complicated.
Much more complicated and not a one-size-fits-all. Okay, another listener is asking, what are those reservoirs made of that they inject water into? And when the site has expired, do they leave that reservoir buried where it is?
Yeah, so I have to say I'm not a geoscience specialist, but as far as I understand it, these reservoirs are porous, so that they contain pores that contain the oil. The oil can flow in the reservoir. It sits there because on top of that porous layer, there is a impermeable layer. That's why the oil has accumulated in that spot. There might be some pressure, so when you drill a well and there's pressure, the oil will just start flowing out. If there's no pressure, you start injecting water, you're replacing oil with water below ground. And then when the reservoir is abandoned, that's the situation ends with.
Yeah.
There's not much else you could do with it.
Yeah, okay. Will the conversion efficiency be improved by recirculation of syngas?
Yes, I think in that process there is a recirculation of hydrogen. Yes.
Okay.
Yeah.
Here's another question that I'm not sure what it means, so we might have to discuss that first. Can anyone comment on the accuracy / feasibility of LI extraction from oil and gas wells brine? That may be out of our scope. I'm not sure. Or maybe it means lithium. We will we'll ask that person to clarify what they're asking, and we'll try to get back to it. Okay, how viable is it to extract carbon dioxide from the air? Won't a lot of energy be required to route via blowers, I'm assuming, air to, okay. Won't a lot of energy be required to route air to a carbon dioxide extraction facility?
Yes, so it certainly costs energy. You have to realize that it also costs energy to take the CO2 from a flue gas, especially because the flue gas also contains other compounds that destroy the catalyst. So there is a, let's say, an advantage of using air that you don't have those toxic compounds in there. It still costs more energy. I don't know, do you have the final numbers, Joule, current numbers? What I heard, correct me if I'm wrong, is that when you look at the total pathway of synthetic fuel production, 80% of it is going to be conversion. So that's by far the most energy demanding and cost demanding step. 20% is the capture. If you would go to a stack gas and using the concentrated CO2, those capture costs would be half. So on the final price of the final product, doesn't matter so much. I think when you look at taking this to the market, being able to tell the customer that your CO2 really comes from the atmosphere and is really climate neutral is a big advantage, because if you take it from stack gas, it's still fossil fuel, fossil CO2, right? Even though it doesn't matter in terms of the, let's say, the looks, it is taking the CO2 from the atmosphere is going to have an advantage on the market.
Okay. Well, that's a lot, and we've got another whole bunch more questions, but I think we want to go to Joule now, and we'll get to some more questions after you tell us a little bit about life cycle analysis.
Great. Okay, so good afternoon, everyone. The research that I do takes a bit of a systems perspective to these energy technologies, and so I look at the effects that these technologies might have in our energy system, as well as what it will take for these technologies to actually displace our current energy components within our energy system. And so this complicated figure here actually gives you a snapshot and a visualization of what our energy system looks like in a snapshot in time. And so on the left-hand side of the figure are the sources of energy that we consume. So you can see oil and coal are the two number 1 and 2 sources of energy that we're currently consuming. And on the far right-hand side are the final services. So these are energy services that are what we actually want our energy for. So we don't necessarily need oil per se. What we need is transportation service. And you can see that the majority of the oil that we're consuming today does go to transportation services in the economy. And this is a picture of the global energy system. In between the left-hand side and the right-hand side are all the different conversions and manipulations, transportation of the different sources of energy through to their final service. And you can look at the sort of relative contributions by the width of the bars that are being presented. So it tells you the magnitude of each of these different services as well as the sources and their conversion.
And I imagine that little blue renewable at the bottom is bigger today than it was a few years ago.
Yeah, so this is a little bit dated. It is a snapshot in time,
yeah.
So that is growing, but it is important to recognize the place that it has currently. Right?
Yeah.
You'll see that biomass is up near the top as well, so that would be considered a renewable, but here they've separated that out. Yeah. So just thinking about some of the technologies that Marc has mentioned, the type of work that I do actually tries to assess those technologies in this context of the full energy system, looking at the full effect, so whether it's a techno-economic sort of evaluation or looking at the environmental consequences of both the existing energy system as well as how that new technology might play a role and shift this picture of the energy system, which has been changing over time and will continue to change as we move forward. So that's the type of analysis. And I'm just now going to focus in a little bit more on the oil pathway, because that is the predominant fuel source that we use to provide our transportation services. So some of the technologies that Marc has mentioned might displace some of that or might change the way in which we're actually using that.
If we get those electric cars on stage.
Electric vehicles or synthetic fuel production, those kinds of things will play a role in the transportation portion of our energy system. And so what we need to do in order to actually help evaluate these new technologies is first get a handle on what are we doing in the existing system. So right now, the oil in this figure looks like a homogeneous source and would have sort of similar consequences regardless of where you take it out of the ground. But what you'll see in the next figure here is that we, over the last decade or so, we really expanded the sources of oil that we're actually using and processing and turning into transportation fuels. And so that sort of complicates the picture in terms of what are we going to compare these new technologies to. We've got a variety of different ways that we can provide transportation services using oil resources. But whether you're looking at the oil sands or converting natural gas into a liquid form, the consequences associated with that are quite different for these different resources, even the ones that we're accessing today. And so we need to get a better handle on what the consequences of that are. And so a tool that helps us to do that is called life cycle assessment. So it's a decision-making tool that allows you to structure the way you think about complex environmental issues. So this, at its core, is looking across the entire supply chain or over the life cycle of a product, process, or service. So the diagram on the right-hand side sort of shows material extraction, processing, transport, the use, reuse, and then disposal of unwanted residuals. And with this, we can look at the full set of consequences. We can map onto that the economics as well as environmental impacts. And oftentimes, it's helpful to use to look at trade-offs between different environmental impacts. So you can tackle the carbon issue in a particular pathway, but you have to look at the other consequences in terms of things like water consumption, air pollutants, those kinds of things as well. So it's a tool that helps you structure the way you think about those types of complex trade-offs. One thing to note, though, is that the technologies that we're developing, the way that our energy system and our economies are changing, it really has started to demand that these types of tools really get advanced to be able to handle them in better ways. So the traditional use of life cycle assessment is that we would look at a technology that was very close to being commercialized and use that to evaluate the technology to try and identify potential unintended negative consequences, ensure that your innovation is going in the direction that that you're delivering on the innovation that was the purpose of the technology. What we're seeing now is that it's starting, LCA and other types of tools, systems tools are being used to inform funding agencies and investors. So people are starting to look for this type of information about the full consequences of the technology much earlier in the development of the technology itself.
So at the drawing board as opposed to the going to market stage.
That's right, yes. A lot of times getting to the market stage and assessing at that point, it's too late to be able to actually change the process or innovate further to actually avoid some of these consequences. And so really looking for that information earlier in the process. And similarly, policies like California's low carbon fuel standard, the clean fuel standard that was announced at the federal government in Canada, those are also using life cycle tools to be able to map the full consequences across the supply chain. And so because of that, we need to develop better tools to actually do the assessment of those technologies. So particularly on the oil side, because of this diversity of oils and different consequences associated with them, the Carnegie Endowment has led an initiative called Know Your Oil, an Oil Climate Index. And this allows us to look at the greenhouse gas implications associated with extracting, processing, and using different types of fuels that are processed around the world. And this was led by the Carnegie Endowment, but myself and Adam Brandt from Stanford University have contributed to this project. And at this point, so we're in phase 2 of the project, we have 75 global crudes that have been assessed within this tool. And it's an online open source tool, and those resources, the resource actually gets that link, have been posted within the webinar. So you should be able to access that and play around with the tool. It's meant to be, investigated and manipulated, and I'll show you a few examples of that as we go. But the 75 global crudes, we determined they needed to hit a certain threshold in terms of data quality. But collecting this data, all of it is open source and publicly available data. So it does restrict the number of pathways that we've been able to characterize to date. But it does, sort of represent every major global region.
So are there a lot more than 75 different types of crude then?
Oh, yes.
Yeah, okay. So this is like a snippet or a subset of the crude that's available based on the good data that is available.
That's right. Okay. So this is how much we've been able to characterize so far. And even in this, we get representative data for a particular oil field, but some of these fields have been operated for more than 100 years, and so the diversity even within one field, you might, is not fully represented within we've got some proxy crudes and data representing those crudes. But it does represent about 24 million barrels per day, which is about 25% of global production. We continue to develop it and continue to add crudes as we get better data. And as I said, there's open source tools that support this work. So there's the upstream portion is from the OpG model, which is from Adam Brandt at Stanford. I supplied the prelim model, which is the refining side of crude processing. And then we have the downstream module as well from Deborah Gordon at Carnegie Endowment. So we can then characterize the full life cycle impacts associated with these crudes. And I'll just show you an example here. So these are across the entire supply chain. This figure looks at total greenhouse gas emissions. So we're basically looking at extracting a barrel from each of these different regions, extracting it, processing it, transporting it, and using those crudes. And what you can see here is we plotted each of those crudes as a bubble, and the x-axis is just the API gravity, so how heavy each of the crudes are. The different colors represent different categories of crudes, and you can see that there's quite a variety of impacts in terms of the greenhouse gas life cycle impacts associated with these different types of crudes. On the right-hand side, you can see different factors that might change the sort of order or level of greenhouse gas emissions associated with these crudes. And I've got a static snapshot here, but if you're on the website, you can go through and actually change these different factors. So just one example that I'm going to look at is if you look in the sort of top portion of the figure, quite a few of those crudes are high flare crudes, so crudes that are being produced where the produced gas is actually flared, so you end up with additional CO2 emissions associated with that flaring. If you actually turn down the assumption about how much gas is being flared, you can actually see the impact of that on the greenhouse gas emissions. So when I flip to the next slide, you can see that a lot of those emissions have reduced for the crudes that do have high flaring. So we can see that. That's just one example of the types of technologies or changes that could be made within these processes that can affect the net greenhouse gas emissions associated with these crudes. There's quite a few additional options on the right-hand side that would allow you to investigate that. And our phase 3 of our project is trying to add additional opportunities to assess what the carbon mitigation potential might be for these different pathways.
It certainly gives you a sense just in that one slide, the complexity of evaluating all the different factors. Wow.
Yeah, it is complex, and you know what we're trying to do is offer the tools to allow you to understand the effects of that complexity as well. So the next example was just to show that we've got different denominators that you can use to actually assess the greenhouse gas footprint. As I said, this one was presented per barrel of crude. So for every barrel of crude that comes out, what are the full greenhouse gas emissions associated with that? On this next slide, we've actually changed the denominator. So now it's per dollar of value that you actually get out of each of those barrels. And you can see that the pattern of these different crudes is quite different when you change that. So I encourage anyone that's interested to play with the tool a little bit more, and you can look at those differences in more detail. But this really helps to provide the backdrop by which we can then start looking at some of the sort of longer-term moonshot or potential big magnitude changes to our energy system for transportation. We can now layer in what do these new technologies do when we look at the consequences of them compared to the existing system that we have that is quite complex, but now we've sort of got at least an estimate of the greenhouse gas implications associated with that. So going back to thinking through this, the CFRUS project, the Canada First Research Excellence Fund, research that was funded through the University of Calgary, we have two sort of proposed outcomes for this, both the scientific breakthroughs that allow for investigation of opportunities in the energy system, as well as technologies that can actually be commercialized that would realize that potential of the unconventional resources in a low-carbon future. So with that, we have the sort of typical process that we would go through in developing new technologies or investigating the research that would allow for scientific breakthroughs. And the research teams at UC that are actually working on this can actually, go through some iterations in terms of developing those technologies and have some tools available to actually do that assessment. So this is just here the research teams and the types of activities that they would conduct. What we can do on the systems analysis side is actually provide additional information at each stage of the development cycle to allow for additional options, additional information that would help inform decision-making at each stage of that development. So at the concept stage, we can do some additional analysis that might help inform the types of materials that get used in the process. That might help to lead into new experiments that might answer some of the questions that need to be answered as you go through that development cycle.
Brings so much more information to the table, hey?
That's the idea, and the purpose is to try and make this development process more efficient and effective, so that you're identifying where there might be some consequences earlier in the process, so that you're not going down a development cycle that you realize that later, right? So making it more efficient and effective is the goal of the research. And also on the scientific development side, trying to enhance that process by bringing that systems perspective to the scientific development. So just to wrap up then, just going back to that systems perspective, we are developing these new tools to look earlier in the development cycle, but always want to come back to that picture of the energy system and how these technologies could play a role.
Yeah, that is such, that graph right there, or that image right there is just so, it just got so much information packed into that, hey? That you may not think about it if you hop on your car or your airplane or whatever. That's like a remarkable amount of information right there.
When I find that it's helpful to understand the relative impacts associated with different types of activities, right? And then the different types of energy services that we think about. Mm-hmm. And starting from those services back to how do we provide those services in the most efficient and cost-effective way. So just the key points I'd like to highlight then, as we transition to this low-carbon future, I foresee that transition as providing specific and unique challenges and opportunities for both Alberta and Canada. And the cutting-edge research that's being done by Marc Strous and other researchers on campus can really help to enable the discoveries and technologies that will help to support Canada in that future. So allowing the unconventional resource base that we have to be competitive in a low-carbon future. That's really the thrust of a lot of the development work that we're doing. And then that systems analysis then can help to ensure that the goals of innovation are achieved while minimizing potential negative unintended consequences associated with those technologies.
Okay, well, let's get to some questions. There's quite a few of them again. Thank you very much, Joule, for taking us through the next-gen life cycle analysis. It seems like technology or the changes in technology has really pushed your field to change as well.
Yeah, innovation on that side as well.
Innovation everywhere. I love it. Okay, so is warm DME extraction being seriously considered? There's a question that maybe, Marc, maybe that's, again, something that we need to come back to. Warm DME extraction. Maybe we'll come back to that one. Okay. Oh, hang on now. Oh, I'm having a little technical difficulties here.
I guess what it meant is a way of extracting bitumen with a solvent. Right? I think that is the warm DME extraction. I think solvents and additives are part of our project. I think the focus is on additives, so to add things that are, let's say, can be active at a lower concentration than solvents. You know, using solvents would bring a lot of extra CO2 emissions too, but using an additive, so something subtle like soap and water, would I think is the aim.
Okay, thank you for that. I'm sorry for throwing that at you out of the left field there. Okay, Joule, here's a question that someone's asking. They're saying it's a broad question, maybe it's out of scope, but are life cycle assessments being done on the impacts of the transition to a more electrically powered infrastructure? What should we expect?
Yeah, so definitely being looked at not just from the flow of the energy itself, but also from the infrastructure that would be required. And so looking at if you have to double the amount of electricity generation capacity in Canada in order to support a electric vehicle fleet, something on that order. Definitely there are infrastructure issues associated with that, and depending on the source of electricity, that's going to have different types of impacts. I would say, it would likely be, from a greenhouse gas emission perspective, sort of an order of magnitude smaller, the greenhouse gas impact of that infrastructure compared to the actual fuels that are used and what might be offset. But there are other types of environmental consequences that need to be thought about. So if you're looking to supply that electricity using hydropower, for example, the greenhouse gas emissions associated with that are very low, but the local ecosystem impacts can be quite expensive. And so in that case, you would want to look at the full set of environmental impacts associated with that.
Okay, here's another question. In Alberta, we're replacing coal-fired power with renewables, but this requires gas-fired power to provide backup. So we can't deeply decarbonize electricity production without CCS, carbon capture and storage, right? What does LCA say about timing and cost of CCS?
Yeah, so I've been looking at carbon capture and storage for many years now, and it had very different iterations in terms of the discussion of when it might be deployed. I would say that, gas being the backup to intermittency of renewables is one option, right? The other option is a variety of different storage options for that electricity. And so we just last week had a webinar that was talking about renewables and storage. So there's a lot of details there. Right now, a lot of those storage options are relatively expensive. So if you have to build everything today, then you would likely build gas to back up those renewables. But as we put thought into how do we design our systems most effectively, that storage could play a role and could offset that gas in the longer run. I would also say that the switch from coal to gas while not getting us to the deep decarbonization pathways, it still gets us partway there, right? So I don't think we want to neglect the fact that the shift from coal to gas does have benefits associated with it.
Right, okay. Question for Marc. When using an older reservoir for electrical generation, what is a realistic megawatt yield that we think we could achieve? What kind of scale could we reach? Do we know that yet?
It's a very good question, and I think that is going to be the main technology challenge. So we've done the math. It is possible to get more energy out than we put energy in this pathway. But the challenge is going to be to get a significant amount of energy out of these reservoirs. When you look at, let's say, oil, what they call oil cut, so how much oil do you produce while flooding the reservoir with water, can be quite low, right, 5% or even less. But there's still a lot of energy in that when you compare it to quite a concentrated shuttle. So yes, this is the challenge. And I cannot say what the research brings us, right, but it's certainly a very good question.
Stay tuned is the answer there, hey?
Yeah.
Well, and I'd just add as well that scale and the magnitude is one of the targets that's being discussed as we iterate through those concepts. And so the challenge is how do you design the system such that you can get certain levels of power out, but also trying to pair those operations with other types of applications. So you might not meet and get to the size where you're competing against a natural gas power plant. You might not be at that level, but if you could pair it with other types of technologies that might use smaller amounts of electricity, then you might get some unique applications that you could use this for in the near term while you develop the larger power output concepts along the way.
Okay, another question for you, Joule. And you might have to tell me what this question means after I say it. Okay. How do you see the N-Solve and ESIEH for the future of oil sands extraction? Do you consider them promising? First of all, what are those things?
N-Solve and those are the two technologies. So one is sort of solvent-based, and so Marc had talked about the solvent-based. The other one is looking at electromagnetic combined with solvent extraction techniques. And so the use of solvents, in principle, the biggest impact that it has is that it reduces the amount of steam that you need. And so definitely promising from the fact that anything that can help to offset the amount of steam, which requires natural gas to be burned to provide that steam, right? So from a greenhouse gas emission perspective, it is promising. I would say, though, that we need to think about the entire life cycle of greenhouse gas emissions. So while those might be near to midterm solutions or contributions to emission reductions, we also need to be thinking about the long-term contributions. And that's where some of these, lower probability, higher risk moonshot ideas can help to rethink the reservoir completely. So I think they have a role, but they have a role in sort of that near to midterm.
Okay, another question for you, Joule. How is traditional LCA used to inform funding and investors? You've mentioned that you're using it earlier on now to help you with these decisions. How are economic trade-offs handled in LCA?
Okay, so I see those as two separate questions. The first one is a lot of the work that was done early days for life cycle assessment was done for governments, and it was done to inform policy. So it was to decide on the types of incentives that need to go forward in terms of the technologies that might be more promising than others. And so it was done at a very high level and was used to help inform the policies. How that shifted is now it's actually being embedded within the regulation itself. So they're actually measuring for every product that enters the jurisdiction, what are the complete life cycle emissions associated with them. So it's a much deeper representation of the individual pathways rather than, product A versus product B, what are the differences between them. I'd say classically, life cycle assessment has not included economics, and so oftentimes it was just framed to look at the environmental consequences of different products. Now we're starting to look at the economics, and there's a new area of life cycle development that is consequential LCA, and that really takes the economics into focus and allows you to look at the full economic consequences of shifting that energy system in a certain direction. What are the full economy-wide effects of doing that, both economically as well as environmentally?
Okay. Now, Marc, a minute ago we had a question about LI. So someone has written in to say there was a question earlier about enhanced revenue from trying to produce lithium from spent oil field brines. I'm wondering to what degree this has been explored from a life cycle assessment standpoint. This may prove to be an elegant revenue source as we transition away from fossil fuels. What do you guys think?
Do you know about it, Joule?
So I know that lithium is readily available in very small quantities, and so I'd say that that's definitely worth investigation in terms of how we might be able to produce that locally. The consequences of lithium-ion batteries broadly is something that is being investigated pretty deeply, and other types of materials like cobalt that help support that process are also issues that are being raised associated with that. As we start demanding more and more of these materials, that shifts the consequences associated with them. So how we get it out of the ground if you only need a small amount of it versus very large quantities, that is an issue, and it is getting quite a bit of attention from the LCA community.
How does bioenergy with capture and storage compare in technology readiness level and cost with standard petroleum use, commercial capture and storage like Quest Radway? Roadmaps for the Paris Agreement call for immediate deployment to reduce emissions. Can we afford to wait for things like BECCS and air capture and fuel synthesis?
Okay, well, lots of questions in there.
That could be a whole webinar on its own, isn't it?
Let's say, I think a lot of the climate modeling or integrated assessment modeling, so there's lots of scientists who try to predict what happens in the future if we would do this or if we would do that, and what would the effects be for the climate. A lot of those models show that if we want to, keep the warming below a certain whatever limit, we would need these negative emissions. And bioenergy with capture and storage is, I think, the main pathway discussed to realize those negative emissions. There's an extreme amount of criticism on that, and I think it's justified. But when you would use the current ways to do that, it would totally, compete with food production. It would destroy, much of the earth for getting all that bioenergy. And I think that I think there's other, critics saying, and I also agree with them, we shouldn't count on negative emissions. It's unproven technology. So let's just focus on reducing our current emissions and not get, not delude ourselves that someday we'll be able to do that. I totally agree with all that. Still, I think there is potential when we do the cost projections, and Joule and I have collaborated on that. We think that it should be possible to produce natural gas with our bioenergy approach for a cost of about $10 per 1,000 cubic feet. I think that's a reasonable starting price to start scaling up. It's much more expensive than the gas prices in North America at the moment, but it is comparable to the gas price in Europe. So I think the idea is not totally outrageous. I think there's also very interesting developments in designs for oxy-fired, oxy-combustion of natural gas that would enable quite cost-effective sequestration of carbon below ground. So there is potential, and we're working on it. Shouldn't be excluded, but should also not be counted on.
Okay.
If I could just add to that the energy systems models, there are quite a few jurisdictions where when you start actually trying to look at the most cost-effective carbon reductions, that you have quite a number of things that will come in at a lower dollar per ton cost than CCS on fossil-based systems. What most of those, the energy system models show is that at some point you need to start moving to those carbon capture and storage applications, but that you might have a decade of lower cost mitigation opportunities before you go to the CCS options. And so I think that also gives some window of opportunity where some development on the carbon capture and some learnings from projects like the Quest project could help us to help reduce those costs even further.
Okay, we're running out of time here. There's so many questions, but there's one here for sure I want to ask you, Marc. Someone has asked, and we don't have a lot of time to get into the detail, although we could probably talk about it for an hour. We're going back to your research. What are shuttles? Would these shuttles help the microbial process? Would shuttles be similar to catalysts? Are shuttles recyclable or reused?
Yeah, so a very good question. So a shuttle, for example, is iron oxide. So this would just be the rust on your whatever door frame. So they are particulate small particles of iron, red colored. The iron is in the 3+ oxidation state, so it has the potential to accept an electron. So what the microbes do with the rust is they respire it, they breathe it, just like we breathe oxygen. And the product of that is just dissolved iron 2+. So the iron has now accepted an electron. That's why we call it an electron shuttle. It brings the electron up to above ground, and yes, it can be recycled in a fuel cell. The iron 2+ would get reoxidized to the rust, and the electron would ultimately be transferred to oxygen. So it's a fully recycled electron shuttle.
Okay,
brings the electrons up. It's public transportation for the electrons.
Okay, so another question here. Some geoscientists say that CO2 concentration is a consequence of natural warming, not the cause. What are your thoughts?
Okay, so let's see. I'm going to bring back this slide I showed you about that. So that's certainly true that that CO2 in the air and the temperature of the Earth are both influence each other both ways. But you need quite a long geological time for that feedback to occur. What we see now is that the warming is following the CO2, right? The CO2 concentration in the air has exploded, but we don't see a lot of warming yet. So I think that's clear from this graph that also shows the temperature projections. The temperature is not yet there yet. Yes, it will follow. So there is, let's say, the evidence at the moment indicates that that in this case the warming will follow the CO2. I think, among these questions, climate change, I think a lot of emotions in that debate. I think we should look at it very neutrally. I think, there's uncertainty, but I think uncertainty is something we can deal with, right? I think big oil companies also take risks and have a way to deal with those risks, same for insurance. So I think that's the way we should look at it. Global warming is a risk, and research like this is one of the ways to mitigate that risk.
All right, one final question, you guys. When will we be able to leave carbon behind?
Yeah, it's difficult to say. What we can say, the infrastructure we're talking about is so big. It's such a big system. It will move slowly. Still, that means that during your lifetime, if you're in your 20s today, you'll see a lot of changes over the years, I'm sure.
Yeah, I'd say that I think this is a good way to segue through the focus so far today has been on the technology development and even how do we assess that, but I think you can't discount the rest of the factors that influence these types of transitions. So the policies, the level of commitment globally to reducing greenhouse gas emissions, things like that, are going to have really big influences on how quickly we move down these pathways. The researchers at UFC are working really hard every day to try and move these technologies forward, but you also need that pull, and oftentimes that pull comes through policy. And so those types of factors, I think, are going to be pretty dominant in determining that time frame.
Yes, again, stay tuned. Much to see in the coming years and decades how this all plays out for sure. Thank you very much, both of you, for coming and bringing all your expertise to us today. We really appreciate you taking the time to join us and join all our listeners. So thank you, and thank you to everybody who participated and who sent in questions. If you have a minute, please don't forget to fill out that survey, and also check out the resources, the Know Your Oil Index. You could probably spend several hours or days with that, just getting to know the different factors that go into it. So take a look at the resources. Please fill out the survey. Sign up for other UCalgary webinars. Download our ebooks. Watch our videos. Check it all out at that link right there, ucalgary.ca/explore/collections. There's much information there. And we're bringing you more information, a couple of webinars coming up. One about climate change in Canada's Arctic, impacts on Inuit communities and marine systems. That's June 15th, so mark that in your calendar. And then on June 20th, energy and the environment. Are our laws keeping up? So lots to learn there. If you have ideas for some other webinars you would like, other topics of things you would like to learn about, please email us and let us know, because we would like to bring you as much information as we can from our brilliant scholars like Marc and Joule who've joined us today. Thank you again, everyone, for tuning in with us. My name is Jennifer Alford, and we'll see you next time.